Hello, December the 12th. Let's get started on problem 21, where we will assemble problem 19 and 20 to find the zeta function of this kind of elliptic curve. NR I have taken from problem 19 the number of points on the elliptic curve, which we are going to prove has a particular form. So we set this, I'll take another color, to be alpha, and that means we have n1 equals p plus 1. Oops. Alpha actually contains this as well. Plus alpha bar. Now, why is that minus? They have put up a minus here. We need to take that into account. So this minus gives minus alpha bar, and then it ends up in the numerator. These two end up in the numerator of the zeta function. Now we have to use n to find nr. So q equals p to rth, and then chi2 point r, we use the norm of the if q is an extension of fp, so there is a norm going this way, and that's the map we use, and the same with 3. We choose the one defined this way. Now let's go back to black. And that means we have we just take the blue part here, chi2r of minus a, chi3r of a, comma, and we're going to use that was my phone. The Hesse-Davenport relation minus g of chi times the norm from r equals minus g of chi to the rth. That takes and that's interesting. What does that really take care of? You see, I didn't study that conversion properly. I thought it would be obvious how to use the Hassan-Davenport relation, but it's far from. dA depends on the on problem was it 18, and these values of chi. Oh, A actually lies in Fp, so the norm of them is A to the pth, A to the rth. So we'll have to do it one at a time. Oops, the norm of minus A to the rth, which we can put out here. All right, and chi3 of R of A, well, that's the same. All right, so the dAs I'll just have to write the formula from that was problem 20A. But this is chi2 and chi3, so we can't use that. Well, one obvious attempt is to try to use the definition. That becomes complicated. So, time for a break where I read the derivation in the theory, and then we'll hopefully be able to apply that. All right, in the theory section, they use formula 3 for the in the start of the section, it's g chi2, g chi3 divided by g chi2, chi3. That's it. and that's this minus, there are 3, so it's altogether a minus. Now, where did that come from? Oh, it should be minus to the rth. This part with chi2r and chi3r, we call it alpha r. And then this was a minus. So we have alpha r equals, and then minus to rth. Oops. That comes from here, and this minus is in from here. And then we get this part to the rth, this part to the rth, and this part to the rth, so that's alpha to the rth. And that was exactly the formula of the book. And the complex conjugate will, of course, agree. So in R, it's Q plus 1, that's P to the rth plus 1, minus alpha to the rth minus alpha bar to the rth. And that was what we should prove. That was A. In problem B, we have the case P is equivalent to minus 1 modulo 3. And then we take the non-trivial characters where Q is P squared. So all of this machinery works. First, prove that they are both trivial on elements of Fp. Well, when P is equivalent to 2 modulo 3, x mapping to x to third is 1 to 1. So all members of Fp, Zp are cubes. So chi3 of them must be equal to unity. And chi2 oh, that's obvious, because we are in P squared, then they are all squared in Fp squared. You can think of the quadratic symbol, which simply is plus minus 1, and then in Fp squared it's the square, which is always plus 1, so they're all squares. So chi2 is trivial on Fp as well. This I need to do on a new page, so I'll just make a break, make a cup of coffee, and then write the formulas we need to do it. I did make my coffee, but I stopped dead in my tracks because by problem 19, alpha should be defined this way. And we did something different here, or where was it? Here, defining alpha, chi2, chi3. But in the problem, it's something different. And I didn't show that they were connected in any way, which they may or may not be. I'll just turn on some light so that I don't look like a ghost. That's better, back from the dead. So we need to work a little on this guy, and I have no idea how to do that. Oops. Then we have to do it slightly better. Chi2, df chi3, df chi2, chi3. And if we want to do the same thing that they did in the book, then we have to write j chi3 chi3 by the same way. And g chi3 bar, that is not necessarily the conjugate of g of chi3. Well. So that was the thing I had difficulty with. I'll first extend this fraction so we can just take out g3 or j of chi3 chi3. We need g of chi2 squared and we need g of chi bar chi3 bar and then we can take out this. That's a bad color. They are the ones we will be needing. G of chi2, chi3 bar, d of chi3. I'll just take the formulas 1, 2, 3 in the beginning of the section. to see if we can do anything. G of chi, G chi bar. That's good. Well, that's about all we have, all we've got. We need to get rid of this guy. I don't know how to do that. I'm stuck here, so it's time for a break. Today is December the 15th and it's 5 o'clock in the morning. I played tennis yesterday night and often I awake during the night being very thirsty. I just need a break and have some more water. I ended up not really understanding how to continue from here, and this should be a multiplication, led me to work on chi 6, but that led to nothing. And then when I awoke tonight, it suddenly occurred to me that there was a problem that surprisingly led to chi 2 appearing. And I found it, so that means we don't really need all this. It's problem 6. I should, of course, have written that formula. J of chi 2 equals chi of 4 times j of chi point chi, comma chi. That was a formula that could actually have been used in the theory section, setting chi equal to chi 4. I think that would have made it a little easier. And here we can use it with chi equal to chi 3. So it becomes chi 3 of 4, or the reciprocal of it, times j of chi 3 point chi, comma chi 3. And now we need to compare with what we should get. That's on the other side. It's minus chi of minus a, chi 3 of 4a. Oops. Now, what is that? Oh, I could just use, I didn't need, this is not necessary. So, right. We know this guy is equivalent to minus 1 modulo 3. And that means that alpha must be chosen to be equivalent to chi 2 of minus a, chi 3 of 4a modulo 3, and this is a unit, a power of, a unit in z extended with omega. So there will be two possibilities, and since we use the alpha and alpha bar symmetrically, that's no problem. Now we come to N2. So we need to find out. I'll just write up what we know. So we are in the case of computing N2, where Q is p squared. And then alpha, of course, is equal to the square root of p. And we need to find out what this guy gives in that case. Chi 2 since we are in p squared, then this is always equal to unity. So the question is, how about being a cube? This should be independent of A. I don't think very clearly now. I'll think it through, making a break, and then turn it on again. This is very simple. When p is equivalent to -1, we know that x maps to its cube is 1 to 1. Meaning that 4a is a cube, so this is equal to unity. Therefore, we have to choose a guy which is equivalent to unity modulo p, and that is, of course, minus p, because p itself is equivalent to -1. Good. And now I have used alpha for this as well, but going back to p itself, we take the square root of minus p, and we can use plus minus, both work. So let's check. I'll just compute all of this. No, I don't think that's neat. So I counted the points, number of points on, and that's affine points for p equals 5, 25, etc. And it agrees exactly with that formula. And it is independent of the radius, whether it's 2, 3 or unity, that doesn't matter. That was the first one. The second one, that's 7. And I believe that's problem C. Well, there's not much to say here. It follows from of the first section from problem 2 in the first section of chapter 2 by the work we've just done. But I would like to check it. And I would like to check it with my computation of points of order 7. That means that we have to compute this in and it depends upon A when P is 7. I need to make a table of chi2 and chi3, write up the formulas and check that we get the right result. That will take a little while, and there's no need for you to see me doing that, so I stop the recording and do the work and then show you the result. 4 o'clock in the afternoon. I worked a little on the Maple script, then I got tired and slept an hour. Breakfast and had a lot to do, and now it's time to look at actually I've been thinking about it a while, as you shall see. First we define the character of order 2, which is easy. To make the character of order 3, I want the log Q. So first we do the powers, and then when we sort it, we get the logarithm. This is the exponential map. And then we can define the character. And it's symbolically, and we use W instead of omega. And then just to check that it's right, the generator maps to omega, and 3 squared, 9 equals 2, P is 7, omega squared, 2 times 3 is minus 1, which gives unity, etc. Then we compute the coefficient to j chi3 chi3. So that's omega unity minus omega squared, minus 1 minus omega. And 7 splits into this product, for instance. You can see they both have norm 7, 9 plus 1, that's 10, minus 3, 4 plus 1 plus 2, both 7. And for reduction, the two formulas reducing omega. Now what is this? That's the... So I choose one of these guys. Where did we have the factorization? Oh, here. We choose one of the guys, 3 plus omega, and see what are the... multiplying it with the 6 units. So we have the 6 equivalent generators of the ideal. And now we just take radius 1. So we have A equals 1, that gives omega. So we must search here to find 1, which is equivalent to omega modulo 1. And that's the first guy. 3 plus omega is, modulo 3. And then we use the formula, and alpha bar, we just substitute omega with omega bar or omega squared and compute the result. That seems fair enough. We do the same with 2. I'll just show it. It's where was it? 2 here, that's unity. That's it, minus 2, minus 3 omega. That's what we use. And get this sequence, etc. all the way up to a radius of, how much was that? 5. Actually, it did up to 6. There are 6, yes. And now we compare them, and they disagree. On the other hand, 238, 320, that one we have here. The second, that seems to fit. The third disagrees as well, but it occurs here. So something is wrong. And of course, what's wrong is that I'm using the wrong ideal, or the wrong factor of 7. But why? The only reason I could think of was that we should use problem 20, part D, and then use the character of problem 20D. All right. That makes sense, because we have two factors of 7, each having 6, when we multiply with the units, 6 distinct generators, that's 12 altogether. 2 of them will be equivalent to -1, or whatever it needs to be equivalent to. And I just was lucky enough to choose the wrong one. That is a 50% chance, which made me able to handle these problems. Otherwise, I would just have thought that everything was okay. But I failed, and thank you for that. And the problem was that I totally misread problem (20e). We have to do that. So we define chi of x defined by x to p minus 1/3 modulo some ideal So 7 splits into ideals. So we go modular this ideal. And then we need to show that using this guy, is equivalent to -1 modulo 3. Is that true? I didn't think that was. Yeah. No, we have to show that it lies in the ideal P1. That's something quite different. So it's true that modulo 3 is equivalent to -1, but we have to show that it lies in this ideal. That's the point, and I totally missed that. This guy we call C. And we are in ZP. So we need to show that this vanishes. And actually all these guys lie in ZP. X runs through ZP. So we can just show that it vanishes modulo P. And then we use the binomial formula. And exchange sums here. minus to ith can come out. And so we'll sum over the x's. The point is that I plus c is positive and smaller than p. Actually, I and c go up to c, then 2c, that's smaller than p minus 1. And in set p, all the or the multiplicative group, the minimal or the polynomial they satisfy is x to p minus 1 minus p minus 1 minus 1 vanishes, and that means that all the symmetric polynomials vanishes, except, of course, the product of them all. And that means that all these minor sums, even if we take 7, then we come up to 4, and it's S6 that fails to vanish. S5 still vanishes. So these power sums vanish, so that just vanishes. And that is, of course, modulo 3, modulo p. So this sum vanishes in set p. So of course it vanishes why does it so? It was obvious earlier, now I can't see it, but leave that for and now we can do it right. So I prepared it. This is the guy we must use, which agree with our character. I actually haven't verified that. And the units we have here, or the generators of the ideal we have here, and the list of coefficients. So minus omega that we have here, 3 plus 2. That fails to agree. Damn it. One, it gives minus omega. Let's take the next. It gives minus 1. We have that here. Minus 1, minus 3 omega. That fails as well. A little break while I figure this out. I'm sure it should be easy to find the mistake. it appeared I'd copied the wrong list of the coefficients. That doesn't work while I'm recording, so let's just forget all that. So the first one should be equivalent to omega. Here we have it, minus 3 minus 2 omega. What am I? Oh, it's still because it can't understand alt. Let's try once again. That was. It agrees. I'll just make a break and do the rest and show you that they agree as well.